Hello, welcome back. This is the third video for chapter 6. After this video, you supposedly can answer tutorial question number 5. Let's start with the first equation. According to this equation, we can say that this refers to a heterogeneous equilibrium because it involves more than one phase, which are solid and also aqueous. And based on this equation and also the physical state given, we only able to write the Kc expression, but we are not able to write the Kp expression due to gas phase substance is not appear. Now let's check with the second equation. If I write the second Kc, this will be the answer. And now let's check. The second equation actually is the reverse for first equation. So now let's check what's the relation between Kc forward and also Kc reverse. Before continue, I will make this as first equation and then this is the second equation. So now we want to prove, is this third equation correct? Okay, so now I'm going to substitute second equation into third equation. Then we will check the third equation will be similar with first equation or no. Okay, equal to 1 over concentration of silver to the power of 2 divided by the concentration of zinc ion. As mathematics, I will maintain 1 over will become multiplied and then reverse the position of the zinc ion and also the silver ion. Now I check this one and then this one supposedly is equal to Kc forward. So it is similar with the first equation. Now look at the third one. Again, we compare the third equation with the first equation. We notice it is reversed. At the same time, the coefficient is 2 times. Or another terms that we can say, this is the double of second equation. So how are we going to write the Kc expression for equation number 3? You will notice here will become silver to the power of 4 divided with the concentration of zinc to the power of 2. So if now I want to relate this with the second equation, the Kc for the second equation, it will become equal to Kc silver ion to the power of 2 over zinc ion. Then I can make a bracket and then it's to the power of 2. So if 2 times 2 here will become 4, 1 times 2, the power here will become 2. So it's exactly same with the one that we write. Okay. After we know how to write the Kc expression and also relate with the previous equation, we can do the calculation. Let's look at the calculation in the second slide. Alright, after knowing how to relate the Kc expression with the chemical equation given with different coefficients, then now we can try to answer question with calculation. In this question, according to this chemical equilibrium, the Kc value given is 2. So after I write the Kc expression, I consider this one as Kc expression for the original equation. So now I will going to write the Kc expression for equation A, which I label like this. I put A here so that I will not confuse. Based on this equation, the Kc for A will be concentration N2O4 divided with the concentration NO2 to the power of 2. So if I'm comparing this equation Kca with the Kc original, I will notice it actually is 1 over Kc original. Okay, at where the position is interchange each other. So then, due to I want to calculate the value of Kc, so I'm going to substitute the Kc original, which given in the question is 2 over here. So press the calculator, we will get the Kc value is 0.5 molar. Next, we are going to look at the Kc expression for equation B. According to this will be concentration NO2 divided with the concentration N2O4 to the power of 1 over 2. So if I check the relation between Kcb with the Kc original, basically I will notice that it is Kc original rise to the power of 1 over 2. Do you agree? 2 times 1 over 2, I will get 1 here. 1 times 1 over 2, I will get 1 over 2 here. So now for the Kcb, 1 over 2, the power of 1 over 2 here is similar with the square root. So that's why I will put square root here. So the answer will be 2 square root. Okay, press the calculator, you will get the answer. Okay, hopefully with these two slides, you will have the idea how to answer tutorial question number 5. Okay, in this slide, we are going to relate the Kp expression and also the Kc expression with the ideal gas equation. Before we go in details, we are given a general equation. Based on this general equation, we know that this is homogeneous equilibrium because it involves all the gases. And due to the presence of gases, so it can help us to write the Kp expression and also Kc expression. Now we are going to relate with the ideal gas equation, PV equal to nRT. If you notice, if we move the volume to another side, I will get number of mole of gas air divided with the volume multiply with the RT, at where N over V actually is represent the concentration. At where I will write like this, Ca is represent concentration. Let's continue to next slide. Alright, let's continue from the previous slide. This is what we get from previous slide. Okay, I label this as the first equation. And then this is the Kc expression. And then this is the Kp expression that we get from previous slide. So now, according to this statement here, substituting first equation into the Kp expression. So let's start with the Kp expression. Okay, so now we check here. This is partial pressure C raised to the power of x. So because of we will replace the partial pressure C with this, so that's why at here we will see concentration of CRT to the power of x. So if this one is partial pressure for D, here we will show concentration of DRT to the power of y divided with the concentration ART to the power of M, then multiply with the concentration BRT to the power of N. Next, we are going to factorize because we notice RT, RT, RT are similar. So once we factorize, this will be the expression that we get. So now you will notice this part is similar with Kc. So we will end up with this Kp equal to Kc, and then make the bracket Rt. This one is another factor that we can factorize. Rt. Okay, and then here will be x plus y minus m plus n. Y here is minus because it is dy. At where, if based on the general equation that we use, this one will be considered as delta n. So delta n, we can general to say this is total number of mole of gas for product minus with the total number of mole of gas for reactant. So this is how we can show the relationship between Kp with the Kc. This is the formula how Kp equal to Kc Rt delta n is derived. As usual, after we know how to derive the equation, then now we are going to look at how to apply the Kp equal to Kc Rt delta n in answering the question. Given Kc for the decomposition is 0.36, so means that Kc value is given. Determine its Kp at the same temperature, so we need to find out what is the Kp. Okay. Determine the formula that we want to use, then substitute the correct value. Kc given in the question is 0.36. R is still standardized as the ideal gas equation, 0.08206. Since we are going to use this gas constant, atm liter per mole per Kelvin. So the temperature also must be in the unit of Kelvin. 25 degrees Celsius mean is 298 Kelvin. So just now we already have the idea. Delta N is mole of gas for product minus mole of gas for reactant. So for the product there is 2 mole, but for the reactant there is 1 mole. So that's why here is showing 2 minus 1. Then now you can press the calculator and you will get the answer. Kp is 8.8. So with this, I'm going to finish the video. So basically, in this 1 hour, we are going to consider done for question 6.1. At where next week in our lecture, it supposedly will continue with the calculation about ice table. The ice table is not referring to the ice that we make from the water, but the ice table, the I is stand for initial, C change for changes, and the E is stand for equilibrium. So before that, please answer the quiz shared in the Microsoft Teams. The quiz will be consider your attendance for this this 13th of November 2020. And then please answer the question before next Wednesday. Okay, I know some of you maybe are preparing for the Deepavali, so maybe you are not free to watch the video on Friday. So that's why I allow you to watch the video from Friday up to next Wednesday, which is 18th of November. For those who celebrate Deepavali, wish you have a happy Deepavali.